You grab a steaming mug and your skin instantly screams hot. But is it actually telling the truth? Picture 3 bowls of water sitting on a table. One is filled with ice-cold water, the second is comfortably warm, and the third contains strictly room temperature tap water. Imagine plunging your left hand into the icy bowl and your right hand into the warm one. You hold them both there for 30 seconds, letting your skin adjust to these extremes. Now, pull both hands out and dunk them together into the neutral tap water. Your left hand will suddenly feel like it is in hot water, while your right hand feels like it is freezing. Your hands are sitting in the exact same bowl, reporting 2 completely opposite realities. Our nervous system only detects a change from its previous state. Biologically, we are incapable of feeling absolute temperature. To find the truth, we have to separate what we feel from what is actually happening. Heat is an invisible form of energy that strictly flows in one direction, from a hotter object into a colder one. Temperature, on the other hand, is the precise numerical measurement of that heat energy. This diagram shows how matter behaves at a microscopic level. Temperature measures kinetic energy. In a hot object, particles are ricocheting and vibrating rapidly. In a cold object, those same particles are slow and sluggish. Because this microscopic motion is invisible to the naked eye, and our skin is so easily tricked, we had to engineer specialized proxy tools to translate that microscopic motion into reliable numbers. The traditional glass thermometer solves this problem using a principle called thermal expansion. As the invisible kinetic energy of heat transfers into the glass, the liquid inside, usually mercury or colored alcohol, expands, forcing it up a very narrow tube. But not all thermometers are built the same. The clinical thermometer is a highly specialized piece of engineering designed for one specific environment, the human body. This graphic shows the clinical thermometer. Its narrow scale, 35 to 42 degrees Celsius, covers the biological window of human survival. A kink just above the bulb stops the liquid from falling back down, freezing the reading in place for a doctor to log. By intentionally restricting its measurement range, this tool trades broad utility for extreme accuracy and practical medical safety. In the lab, scientific experiments require measuring far more extreme states, like violently boiling liquids or freezing gases. This image displays a laboratory thermometer. To capture extremes, its scale stretches from -10 to 110 degrees Celsius. It lacks a protective kink, so if pulled from a hot beaker, the reading drops immediately. It must be read fully immersed. The mechanical design must match the physical environment. Subjecting a clinical tool to laboratory extremes would likely shatter the instrument. A rising line of liquid or expanding metal is useless without a standardized system to translate that movement into universally understood numbers. This animation illustrates the 2 most common scales. Watch how they anchor to the natural world. When water freezes, the Celsius scale marks it at exactly 0, while Fahrenheit logs it at 32. When that same water boils, Celsius hits 100, and Fahrenheit registers 212. The ultimate scientific standard adds a third pillar, Kelvin. It starts at absolute 0, which is 0 Kelvin. This represents the absolute physical limit of cold, the theoretical threshold where all microscopic particle motion entirely ceases. Together, these scales form the universal alphabet of physics, giving researchers across the globe the same language to measure and communicate the transfer of heat. This precision forms our first line of defense in medicine. Before complex diagnostics, capturing an accurate body temperature dictates how a doctor treats a patient. Beyond the hospital, specialized thermometers track subtle atmospheric changes to predict weather patterns. They guide researchers, allowing them to safely navigate and survive the most hostile, freezing environments on our planet. This diagram outlines a maximum and minimum thermometer. By physically recording the daily extreme highs and lows in a U-shaped tube, this specific tool makes long-term climate tracking possible. While our skin can only react to sudden changes, these engineered tools and universal scales provide the objective data we need to track, predict, and navigate the physical world around us.